Welcome back to the Deep Dive, the place where we turn the densest sources into the sharpest knowledge. Today, we are undertaking a highly critical, and I mean high-stakes, mission. We're moving beyond just general knowledge, beyond common sense, and executing a deep dive into the absolute foundational doctrine of electronic safety.
That's right. Our goal today is, well, it's simple. We are giving you the professor-level cheat sheet. If you're prepping for a certification exam, or maybe you're drafting a critical policy memo for a high-risk environment, you're going to need precision.
Exactly. Not just the why, but the how much.
Precisely. We'll supply the exact numerical thresholds, the precise definitions for medical events, and the strict critical administrative control structure that's known as the tagout bill.
I really appreciate that focus because so often in safety training, people just stick to the common sense stuff, don't stick a fork in the toaster. But we need to know what happens when things go wrong at the micro level. So we're structuring this into 4 robust pillars today. We'll start with the physics of electrocution, what we're calling electric shock. Then we'll move into the preventative actions, the IIG method.
And after that, the granular measurement procedures, and finally, that essential administrative control system, the tagout bill.
Right.
Think of this as building policy from the ground up. You have to start with the immutable physical laws. So we have to prioritize numbers like current thresholds, definitions like fibrillation, and the clear chain of cause and effect. That's what's necessary for sound, safe procedure. This isn't just theory. This is life safety.
Okay, let's do it. Let's unpack this crucial first pillar, electric shock.
Let's get into it.
When most people think about electrical danger, they immediately focus on voltage. They look at a wall socket, 120 volts AC, or a massive power panel, maybe 480 volts. But that focus on voltage, that's actually the first and most critical misconception we need to dismantle right here.
It absolutely is. We have to start with a precise definition. Electric shock, according to the source material, is the sensation and resulting muscular spasm caused when electric current passes through the body.
Okay, so the spasm and the sensation.
Yes. And the source material is, well, it's adamant. Current is the agent of shock, not voltage.
Wait, okay, I want to push on that for a second. Doesn't high voltage still feel more dangerous? I mean, we're instinctively terrified of a sign that says, danger, 10,000 volts. If voltage isn't the killer, why warn against it so heavily?
That's a great question. High voltage is essential because it creates the potential for harm. Think of it like water pressure.
Okay.
The voltage is the pressure in the pipe. But the actual damage, the thing that makes you wet, is the flow of water. You can have 1,000,000 volts, but if there's no low resistance path for the electrons to flow through you into ground, you won't feel a thing. It's the flow, the amount of current, measured in amperes that actually matters.
That makes perfect sense. The pressure needs a path to become a flow. And we have a perfect, if unfortunate, illustrative example from the military mishap reports, the case involving an ET3, a third-class electronics technician.
Yes, that one's a classic teaching case. This individual was working near the RF turret assembly of a high-frequency transmitter.
And the voltage involved in that specific incident was, what, 1,000 volts?
A staggering 1,000 volts of direct current, DC. The technician was making an adjustment, and he removed a high-voltage insulation cover. As he was working, his thumb just brushed the power amplifier two-plate connection.
And that was it?
That was it. That 1,000 volts DC immediately found a path through his thumb, down his forearm, and then to ground. The result was a very serious shock.
So the key takeaway here for any policy review is that the 1,000 volts created the potential for harm, sure, but the biological mechanism, that sudden muscular contraction, the sensation, was directly caused by the current flowing through his internal tissues.
Exactly. It's all about completing the circuit and the resulting flow.
So to properly assess risk then, we have to look past the voltage and focus on, I think the sources said, 4 critical factors that determine the severity of any shock.
Yes, 4. These are the determinants you need to memorize for any exam or policy memo. Number 1, the amount of current flowing through the body. That's the most immediate danger. 2, the path the current takes through the body. 3, the amount of body resistance to the current flow. And finally, number 4, the length of time the current flows.
I find number 2, the path, to be particularly chilling. If I'm designing a policy, I really need to know why current passing from hand to hand is so much more dangerous than, say, hand to foot.
It's anatomy. The body's vital organs, your heart and your lungs, they lie directly in the path between your left hand and your right hand.
Right in the middle.
Right in the middle. When the current crosses the chest cavity, it drastically increases the likelihood of ventricular fibrillation and respiratory paralysis. If the path is, say, hand to foot, the current bypasses the heart for the most part. It can still cause severe localized burns and nerve damage in the limbs, but it generally gives the victim a much higher chance of survival.
So policy should always aim to prevent that hand-to-hand path. We'll get to how later, I'm sure.
We will. It's a key part of the measurement section.
Okay, this brings us directly to the numerical thresholds. These are the absolute data points you must internalize for any exam or policy development. We're measuring in milliamps, right, MA, at 60 hertz AC, which is the standard utility frequency here in the US.
That's right. And we're talking about unbelievably tiny amounts of current causing massive physiological damage.
And why 60 hertz specifically?
We measure at 60 hertz because it's the standard frequency you encounter in most workplaces, but it's also, unfortunately, the frequency to which the human heart is most susceptible. It hits a kind of resonant vulnerability. So let's list these thresholds, starting from the sensation and escalating, well, very rapidly to fatality. At 1.1 MA, that's the perception threshold. It's a slight, almost ticklish, tingling sensation. At this point, you know you've touched something live.
Okay, just a little buzz.
Right. But then at 10.0 MA, this is the beginning of the can't let go limit for an average smaller person, maybe around 120 pounds.
What do you mean can't let go?
The current causes involuntary muscle spasms in your hands and forearms. Your muscles lock onto the conductor. You are now a prisoner of the electric source. You physically cannot open your hand to let go.
That's terrifying.
It is, and it gets worse. At 16.0 MA, that's the can't let go threshold for a slightly heavier 175-pound person. The variation is just due to body mass, skin condition, but the loss of motor control is the key danger.
So you're stuck. What's next?
18.0 MA. At this level, you can't breathe. This is critical because it can paralyze the muscles in your chest, specifically the diaphragm. It just stops respiration. Even if you survive what comes next, you might still die from asphyxiation.
And the final number?
65.0 MA. This is heart fibrillation. This is the fatal threshold. Rapid, irregular, completely useless contractions of the heart muscle begin. Your heart is no longer pumping blood effectively, it's just fluttering. This is often irreversible without immediate high-energy defibrillation.
Wait, hold on. 65 milliamps. I am genuinely shocked by that number. That's less current than what flows through a typical 100-watt light bulb. We treat household 120 VAC as normal, yet 65 milliamp is the guaranteed fatal threshold.
It is. That right there contextualizes the extreme danger of all electrical work immediately.
Okay, let's apply this to a real-world scenario from the sources. If you accidentally grab a 120 VAC wire and you have an average body resistance of 1,500 ohms, what's the result?
Well, you'd apply Ohm's law. Current equals voltage divided by resistance.
Right, so 120 volts divided by 1,500 ohms. That equals 0.080 amperes, which is 80 milliamp.
80 milliamp. That simple calculation shows that standard household voltage, when combined with typical body resistance, is 70 milliamps beyond the can't let go limit and a chilling 15 milliamps beyond the 65 milli fatal fibrillation threshold.
Wow.
This is why policy has to focus on resistance and current mitigation, not just voltage avoidance. The voltage in your wall is already high enough to kill you.
So the key variable we can impact administratively is resistance. The average body resistance is noted as 1,500 ohms. Where does that resistance primarily come from?
It comes almost entirely from your skin, specifically that outer dry layer of dead cells. But resistance isn't a fixed number.
Right, it can change.
Drastically. If your skin is moist, say from sweat, high humidity, or working in a wet environment, your resistance can plummet, sometimes as low as 300 ohms.
Let's run the numbers on that. That's a huge drop. 120 volts over 300 ohms. That equals 400 MA.
At 400 MA, you're not just talking about fibrillation anymore. You are sustaining catastrophic tissue damage.
Yeah.
This is where the physics turns violent. But here's the crucial cause and effect relationship for policymakers, especially regarding high voltage. Skin resistance reduces to nearly zero when you're handling voltages greater than 240 volts.
Okay, why? Why does that specific voltage, 240 volts, destroy the skin barrier? What happens?
Because the high potential difference creates an electric arc across the air gap as you approach the conductor, or it happens immediately upon contact. That arc generates intense heat, burning right through the skin. It causes deep third-degree burns instantly.
So the voltage itself becomes a weapon.
Exactly. Voltage, at this higher level, stops being merely the potential difference and starts actively destroying the body's natural defense. Once your skin is burned away, your resistance drops to the much lower internal tissue resistance, and the current flow becomes unstoppable.
So the high voltage facilitates the killing current by destroying the skin barrier. Okay, now let's bring in that fourth factor, time. We define fibrillation as that useless, rapid fluttering of the heart. What role does time play in this catastrophe?
It's a massive factor. The longer the duration of the current flow, the higher the chance of fibrillation. Your heart muscle, being electrically excitable, is most vulnerable during a very specific brief portion of its cycle. If the electrical shock persists, it maximizes the probability of hitting that vulnerable window. Regulators even use a formula to model this risk.
So the takeaway is that low current for a long time is just as dangerous as high current for a short time. Do we have specific time-current combinations that are known risks?
We do. For instance, any policy reviewer should know that these extended exposure scenarios carry the exact same risk profile for inducing fibrillation. 21 MA flowing for 30 seconds.
Okay, half a minute.
Or 44 MA flowing for just 7 seconds. Or even 67 MA for only 3 seconds.
So they're all equally deadly, just on different timelines.
They are. This demonstrates why immediate isolation of the power source is always the bedrock of any safety procedure. Every second counts.
Okay, let's do a quick recap of Section 1. To crystallize this foundation, we're saying, if you're writing policy or taking an exam, the target danger number isn't voltage. It's 65 milliamps. That's the absolute fatality threshold.
That's the number to remember.
The policy must also account for two factors that reduce resistance: moisture and high voltage. Anything above 240 V that physically destroys the skin.
That's the core of it.
Now that we understand the physics of the danger, we can move into the preventative policies. This is the template for preventing that 65 NMA flow from ever happening. It's summarized by the powerful essential mnemonic: isolate, insulate, ground, or IIG.
This is your core procedural template. It's suitable for any training manual or policy implementation plan.
Let's start with number 1, isolate. Isolation is securing the source. This is the first and most crucial step. It means removing power to the equipment before any physical work begins, usually by opening breakers or pulling fuses.
But isolation goes beyond just that. You must also ensure all electrical equipment covers, doors, and enclosures are kept securely in place. And if live work must be done, and we'll cover those rare instances later, you have to rope off the immediate area, mark the perimeter, and post explicit danger signs.
So you create a physical and a visual barrier.
Exactly. Warning personnel against entry or, accidental energization.
Okay, second is insulate. This means relying on material science to create physical barriers. We're talking about using tools and equipment that are properly insulated.
Right. And for a policy review, a key part of the maintenance checklist here is the frequent inspection of power cords and extension cords.
Why those specifically?
Because breaks, cracks, or any deterioration in that outer jacket are a primary cause of mishaps. A failure of the insulation exposes the live conductors, creating a potential path to ground right through personnel.
And finally, number 3, ground. This is the engineering solution that leverages the law of physics that current follows the path of least resistance. Equipment must be robustly and verifiably grounded to provide a direct, extremely low-resistance path for any accidental fault current, like a short circuit to the metal frame.
Exactly. And the ground wire serves a dual purpose. First, it diverts that dangerous fault current away from anyone standing near the equipment. Second, it protects the equipment itself from excessive voltage spikes, like from lightning or other external events, by channeling that energy safely away.
Okay, so that's prevention. Now let's move to the immediate action required during an emergency. What is the absolute, non-negotiable, most important rule if someone is actively receiving an electrical shock?
Rule #1. Do not touch a victim who is still in contact with a live circuit or power source.
Never.
Never. You will instantly complete the circuit and become the second casualty. This is not intuition. This is policy derived directly from the physics we just covered. Securing the power is always the first step.
What if you can't secure the power immediately? Maybe the breaker is far away, or it's not labeled, or it's inaccessible. What's the approved action sequence then?
You have to use a dry, insulating material to physically separate the victim from the live circuit or to physically remove the circuit from the victim. And we specify dry insulating materials: a rope, a belt, a wooden cane, or rubber matting.
Why the emphasis on dry?
Because if the victim is wet or if the material you use is even slightly damp, the electrical resistance drops dramatically and you put yourself at risk of becoming part of the circuit.
Got it. So once the victim is free of the current, the administrative procedure is critical. You must call medical personnel immediately. And here's a key policy point. Only individuals who are currently certified should administer CPR if the victim is unconscious and not breathing.
That's a huge point. It emphasizes that in these high-stakes environments, well-meaning but uncertified actions are not sufficient. Training and certification are mandatory prerequisites for any life-saving intervention.
Okay. Finally, we have to acknowledge that in certain troubleshooting or calibration scenarios, policy might require working on energized equipment. This is inherently high risk, so the administrative requirements must be stringent and non-negotiable.
Absolutely. The foundational technical prerequisite for this kind of high-risk work is simple. You must always troubleshoot using the official technical manuals and equipment schematics.
No winging it.
No winging it. You need to know exactly which point you're measuring and the expected voltage and waveform. You can't proceed based on memory or approximation.
And what's the critical administrative step that protects both the technician and the command?
You must notify and obtain explicit, documented permission from the highest relevant authority. That means the commanding officer if you're afloat, or your supervisor if you're ashore, before you attempt any work on energized equipment.
And that ensures accountability.
Accountability, awareness, and command-level risk acceptance for the extreme danger being undertaken. If something goes wrong, the chain of command is immediately notified and involved.
Now let's drill down into the granular steps of voltage measurement. This section is all about detail-oriented, step-by-step procedures, and everything changes once you cross that 300-volt threshold.
It's a massive policy distinction designed to mitigate the risk that high voltage poses to skin resistance. Let's start with the baseline measuring voltage below 300 volts.
Okay, so first, the planning phase. You're setting those wiring diagrams and schematics diligently, marking the location of all test points, and, just as importantly, the location of adjacent higher voltage points you need to avoid.
Exactly, even if they aren't your intended measurement target. Next, the personal security requirements, or PPE check. You must remove all metal accessories, watches, metal belt buckles, rings, including wedding bands.
Right.
Any conductive jewelry could inadvertently complete a circuit, leading current directly through your body. These items must be secured. You also have to wear insulating rubber safety shoes or be standing on approved rubber matting if it's issued.
And the crew requirement is non-negotiable policy. Always have a coworker stand by. You never work alone on energized equipment.
Never. That coworker is not just for assistance. They are your immediate responder. They're trained to know how to secure power and begin rescue protocol the moment something goes wrong.
Okay, now for the actual measurement technique precautions, these are the critical life-saving details.
First, always use test probes that have safety guards or barriers on the probe tips to minimize incidental contact with the live metal. Second, where possible, use insulated alligator clips that can be secured to the test point. This eliminates the need for you to physically hold the probe during measurement. And third, always keep your body clear of any metal parts of the equipment chassis that could be unintentionally grounded or energized.
This brings us to perhaps the most important technique for low-voltage work, and it's a classic example of physics-based policy, the single-hand rule. The rule states that you must try and keep one hand secured in your pocket, behind your back, or holding onto a non-conductive surface while taking measurements with the other.
The cause and effect here is direct and vital. By keeping one hand away from the work area, you physically prevent current from flowing from hand to hand.
Which we already established is the most dangerous path.
Exactly. That path runs straight through the chest, heart, and lungs. So if you follow the single-hand rule and you accidentally touch a live conductor, the path the current takes is from your working hand, down that arm, through your torso and leg, and to ground through your feet. It bypasses the heart, dramatically increasing your survival chances. That one simple procedural rule saves lives.
Okay, that's clear. Now we cross the 300-volt threshold. This is the realm where voltage actively destroys the skin barrier, meaning contact is almost certainly lethal.
Right, and the absolute critical difference in policy here is a firm rule. You must not hold the test probe in your hand while the equipment is energized.
That means we need an entirely new, strict 9-step procedure. This is essential for policy drafting or exam prep, as it dictates the required sequence of action.
Let's walk through it. Step 1, preparation. You follow all the preliminary safety procedures we just defined for below 300 volts, the PPE check, coworker signed, schematics studied.
Step 2, isolation. Ensure the equipment is de-energized. This is non-negotiable. Full mandatory tag-out procedures have to be initiated and verified.
Step 3, mitigating residual charge. Use a safety shorting probe to discharge all high-voltage capacitors. These components can store a lethal charge for hours or even days after the main power is secured.
Okay, that's a big one. Step 4, attach ground. Attach the ground probe of your measuring device first. Why first?
Securing the ground point first means that if anything goes wrong during the setup, the low-resistance path to ground is already established, protecting both the equipment and you.
Makes sense. Step 5, secure test probe. Secure the second or hot probe to the specific test point. This has to be done with an alligator clip or some other mechanical fixture. No hands.
No hands. Step 6, setup meter. Set the measuring device to the correct voltage range and polarity, AC or DC. Selecting an overly low range could damage the equipment or give you a misleading reading.
Step 7, measurement. Now and only now, you energize the equipment, take the measurement quickly, and then immediately de-energize the equipment. You want to minimize the time the circuit is live.
Step 8, double discharge. You discharge all the high voltage capacitors again. This step is non-negotiable. It's a critical physical fail-safe against any residual charge.
And finally, step 9, cleanup. Remove the probes from the equipment.
This step-by-step procedure is the perfect example of a policy designed around managing risk rather than eliminating it entirely. The worker is only briefly exposed to the energized state, and that potential failure point of stored charge is addressed with a mandatory dual discharge protocol.
That depth really helps solidify the distinction. The moment you cross that 300 V barrier, the procedure transitions from how to hold the probe to how to set up the measurement before you even think about applying power.
Exactly.
Speaking of unexpected dangers, safety in electronics extends far beyond high voltage. Modern equipment introduces hazards that might not instantly injure personnel but can destroy sensitive, mission-critical components, leading to mission failure. I'm talking about electrostatic discharge, or ESD.
ESD is the static electricity we've all experienced, the shock you get when touching a doorknob in dry winter air. But for highly sensitive integrated circuits and discrete semiconductor devices, even an invisible discharge below the human perception threshold can cause latent or catastrophic component failure. The source material notes these devices, particularly MOS devices, are extremely susceptible.
So if you're preparing a maintenance procedure or a training guide, you have to include the visual indicators and their recognition. These are the sensitive electronic devices warning symbols, usually a triangle with a hand reaching toward a circle of lightning, or the do not open static electricity cautions.
Right. They signal the requirement for strict ESD control. And the protective procedures are entirely centered on equalization and grounding, ensuring charges can't build up a sufficient potential difference to discharge through the sensitive device.
Okay, so what are those procedures?
1, you have to ground all workbenches, assembly areas, and soldering stations where these devices are handled. This is done using specific dissipative mats. 2, you have to be sure you are grounded, usually via a conductive wrist strap that's connected to a common point ground. This ensures you're at the same electrical potential as your workspace.
So you and the bench are one.
You and the bench are one. 3rd, you want to minimize physical handling of the device itself. If possible, hold ESD devices only by their electrostatic free wrap or conductive packaging. And finally, you have to avoid contact with ungrounded materials like conventional plastics, styrofoam, or common cardboard, which can generate and hold static charges.
And there's a specific detailed protocol here related to the transfer of components. When moving an ESD device, you must always touch the surface the device rests on with bare skin for at least 1 full second before picking it up. Why that specific timing?
That 1 second is the mandatory duration required to ensure that you and the surface have equalized your static potential. It ensures any charge difference is safely bled off to ground or equalized across the materials before the sensitive component, which acts like a tiny sacrificial fuse, can complete the circuit.
Got it. Okay, moving from the static world of ESD to the dynamic world of radiation, we have to address electromagnetic radiation hazards, specifically from RF and laser sources.
These are acute safety risks in any facility that operates high-powered transmitters. RF hazards come from high-powered radio frequency transmitters, large antennas, surveillance radars, communication arrays, and industrial microwave ovens. The danger here is fundamentally different from electric shock. It's not about completing a circuit, but about energy absorption. The danger is RF burns.
So it's a thermal issue.
It's a thermal issue. High RF fields can induce significant currents within conductive body parts or any metal objects you're touching. When this current flows, it encounters the resistance of your body's tissue and it generates heat, just like a microwave oven heats food. This results in painful, deep thermal burns, often internally. any maintenance policy must strictly prohibit personnel entry into defined radiation hazard zones during transmission cycles.
And finally, laser hazards. LASER is an acronym for light amplification by stimulated emission of radiation. It's not just bright light, it's a highly concentrated, coherent beam of optical radiation.
And the danger from lasers is concentrated energy absorption in extremely sensitive tissues, particularly the eye. Laser exposure, depending on the class of laser, can cause immediate inflammation of the cornea and even direct corneal burns. Longer-term or repeated skin exposure can lead to accelerated skin aging and thermal burns. Policy mandates that safety precautions must strictly follow the specific defined class of laser being used from class 1 through 4, as different classes pose vastly different risks.
If the first three sections define the physics and the procedures, Section 5 defines the system of absolute control. The Tagout Bill is the cornerstone of administrative safety in any high-risk electrical environment. It moves us from personal caution to enforceable systemic control.
Precisely. The Tagout Bill is officially defined as the system using tags and labels to prevent unnecessary loss of life or damage to equipment by clearly identifying when equipment is unsafe to operate or requires special caution. It's the documented, enforced means of ensuring isolation and physical control, particularly when maintenance is ongoing.
Okay, so for policy memo writers, you need to know the entire structure. The system relies on 5 distinct documents and tools. Let's go beyond just listing them and understand their purpose.
First is the tagout log. This is the permanent chronological record maintained by the authorizing officer, tracking every single action, tag placement, and removal. It provides accountability history.
Okay, the master record.
Then you have the tags themselves. Caution tags, which are yellow, are used to indicate unusual operational requirements or limitations. And danger tags, which are red, are used to prohibit operation entirely.
They're the last two.
Out-of-calibration labels, which are for testing or measuring equipment that's found to be outside of its tolerance limits. And finally, out-of-commission labels. These are for equipment that's broken, permanently disabled, or just can't be repaired, signifying it's permanently removed from service.
Let's focus on the 2 operational tags. The red danger tag is the highest level of administrative caution.
It strictly prohibits operation of equipment that, if operated, could jeopardize personnel safety or damage equipment. This is your administrative red light stop, do not pass go.
So the prohibition here is absolute. If a danger tag is on a circuit breaker, that breaker is effectively non-functional from an administrative standpoint.
Correct. And the removal procedure is just as rigid as the posting procedure. The tag must only be removed by an authorized person, and only once the required work is complete, verified, and the equipment has been restored to a safe condition. Unauthorized removal is a career-ending or life-ending violation.
In contrast, the yellow caution tag is used as a precautionary measure. It provides temporary special instructions or indicates that unusual caution is necessary when operating the tagged equipment. Think of this as the proceed with extreme care sign.
Yes. And the critical restriction here is that you must never use a caution tag if there is any chance of personnel injury or equipment damage under normal operating procedures.
If that risk exists, you have to use the danger tag.
You must use the danger tag. The caution tag is used when the operational status is altered. Maybe a ventilation fan is disabled, meaning the room might overheat, but the immediate risk of catastrophic injury from normal operation is absent.
Okay, so if the piece of equipment is energized, but its performance is just degraded, warranting special attention, it gets a caution tag. If it presents an acute electrical hazard, it gets a danger tag and must be isolated.
That distinction is key for policy implementation.
Now let's talk about the flow of responsibility. This is vital for policy development and accountability tracking.
The entire system is overseen by the authorizing officer, typically a senior watch officer like the CSO OBU, Combat Systems Officer of the Watch, or the EDO, Engineering Duty Officer. They are responsible for managing the system, for signing, and for issuing the tags.
And that permission requires oversight. They need permission from the commanding officer, CSCO, before establishing a tagout that affects mission-critical systems.
Right. It ensures the person ultimately responsible for the entire platform is aware of any operational compromises.
Okay, so let's look at the actual documentation required on the tagout record sheet. This form captures the entire safety narrative, which is essential for any kind of audit trail. What are the key data points?
They must be filled out with exhaustive detail. First, the log serial no, the sequential number assigned by the authorizing officer to ensure the action is traceable. Next, system or component. You need the official nomenclature, like ANWSC3V. Generic descriptions are not acceptable. Then, the reason for tagout. A concise description like preventive maintenance or corrective action for fault XYZ.
And what about the hazards?
That section, personnel equipment hazards involved, is mandatory for danger tags. It must explicitly state the nature of the hazard. For example, severe shock hazard at 440 VAC, or operation would lead to motor burnout.
Specificity is everything.
Paramount. The location needs to be just as specific. Power panel ID, breaker ID, room number, frame number. You have to list exactly where the isolating boundary is located. And finally, the tagged position condition must explicitly state if the item is on, OF, open, or closed. If a valve is tagged, is it open or closed? If a breaker is tagged, is it on or off?
The accountability flow continues with the physical process of posting and verifying the tags.
Right. Posting requires the initials of the person who physically hangs the tag. And critically, there must be a posting check by initial from a second person.
The two-person rule.
It's dual verification. That second person verifies the tag is correctly placed and the equipment is in the designated position, for example, that the breaker is definitely O-off-F.
And when the work is complete.
When the work is complete, verified, and signed off by the maintenance personnel, the system has to be restored. The final administrative barrier is the watch officer's signature and date time. This is required to certify that all affected systems, switches, breakers, whatever, have been checked, confirmed safe, and returned to their normal operating condition and position. This closure step ensures the system is ready for operation and the administrative safety loop is fully closed.
That dual verification and the final watch officer certification turned the tagout bill from just a collection of papers into a truly robust, multi-layered administrative defense system.
It does. Our final section focuses on the physical safeguards, the materials and equipment designed to create barriers against the numerical threats we defined earlier. For policy review, knowing the specifications is everything.
Okay, we start with personal physical protection. Electrical safety shoes. These shoes are mandated to have non-conducting soles. Crucially, they are rated to insulate personnel from shock up to a maximum of 600 volts. This is your baseline foot protection against common medium-level voltages.
And for your hands, we have rubber insulating gloves, which are rigorously classified based on their protective capacity. It is absolutely non-negotiable for technicians to know the difference between the proof test voltage, what they were tested at, and the maximum usage voltage, the maximum safe voltage for actual use.
Let's review those required ratings, because choosing the wrong class of glove exposes the technician to immediate, catastrophic risk.
Right. Class 00 has a max usage of 500 VAC, or 750 VDC. This is suitable for common 120V residential or office work. Class 0 goes up to 1000 VAC or 1500 VDC. This is essential for safely handling typical primary distribution or heavy industrial circuits.
And then it jumps up significantly.
It does. Class 1 has a max usage of 7500 VAC or 11250 VDC. This is for higher voltage utility or specialized industrial systems. And Class 4, this is the highest class listed, has a maximum usage of 36,000 VAC or 54,000 VDC. This is specialized high-tension protection. Policy mandates you must select the class that comfortably exceeds the maximum voltage you're working with.
Okay, now we revisit the safety shorting probe, which you mentioned in our high-voltage procedure. Its purpose is vital to safely discharge high-voltage capacitors that store energy.
It prevents that unexpected lethal residual shock and prevents the ZAP that happens when a large capacitor holds a charge long after the power switch is flipped.
And the key protocol when using the shorting probe is sequential and deliberate.
It is. 1, you verify power is secured and tagout procedures are followed. Again, that's step 1. 2, you connect the flexible ground strap to the metal chassis, or a designated ground point first. This ensures the probe itself is immediately grounded. And only then do you touch the probe tip to the terminals of the capacitor. The source advises repeating this contact 2 or 3 times to ensure the capacitor is completely discharged.
Okay, beyond electrical risks, noise is a major chronic hazard in many operational environments. Let's look at the numerical thresholds for hearing protection, which is mandated to prevent a permanent hearing threshold shift.
The policy is crystal clear on the mandate. Hearing protective devices, or HPDs, must be worn when continuous sound levels exceed 84 dBA or the peak instantaneous sound pressure level is greater than 140 dB.
Can you explain the difference between dBA and peak dB?
Sure. dBA is the A-weighted decibel level, which closely mirrors how the human ear perceives loudness. This measures continuous, sustained exposure, like the constant sound of a diesel generator. Peak dB, however, measures the instantaneous maximum sound pressure, like the sharp crack of a weapon firing or a loud impact. Both are critical thresholds for preventing inner ear damage.
And if the noise is extremely loud, the protection requirement steps up.
Absolutely. Double protection. That means earplugs combined with external circumaural protectors, what people often call Mickey Mouse ears, is required when noise levels exceed 104 dBA or 165 dB peak sound pressure level. These are non-negotiable standards designed to protect personnel readiness over a career lifetime.
Our final piece of physical safety equipment is deck insulating material, or rubber matting. This provides localized shock protection when working on energized equipment or within electronic repair shops.
It's an additional temporary barrier between the worker and ground. But this material has specific specifications. It must be rated for use in areas where the maximum voltage will not exceed 3,000 volts. It's an effective high barrier safeguard.
But maintenance is crucial.
Crucial. The matting has to be kept absolutely clean, free of dirt, oil, buffers, or abrasive cleaners, and regularly inspected for cuts or cracks.
Why is cleanliness so vital for insulation?
Because cuts, cracks, or even just a layer of conductive dirt or oil destroys its insulating effectiveness. It provides a low-resistance path right around the rubber material. If a mat is found to be cracked or dirty, policy mandates that it must be immediately replaced to maintain that 3,000-volt barrier.
What a rigorous and frankly essential deep dive. We started with the foundational physics, confirming that current not voltage is the killer, with 65 milliamps being the absolute fatality threshold.
That's the number.
We then moved through the procedural IIG pillars, the crucial single-hand rule for low voltage, and that 9-step de-energized measurement protocol for anything over 300 volts.
And we wrapped up by codifying the administrative and physical defenses. We now understand the specific procedural purpose of the yellow caution tag versus the red danger tag, and the specific numerical ratings required for physical safeguards, whether it's the 600V electrical safety shoes or the mandate for hearing protection starting at 84 dBA. This knowledge is your policy toolkit. It's designed to protect personnel and mission readiness.
So to bring this comprehensive body of knowledge back to a real-world policy application, the Tag Out Bill provides rigorous signed procedures for managing acute danger, but signatures and initials can be faked, they can be forgotten, or bypassed under pressure. Given that unauthorized removal of a danger tag could result in death or catastrophic equipment failure, what specific policy safeguards, beyond merely authorization and a signature, are most essential to prevent a deliberate or accidental policy bypass in a high-pressure or time-critical scenario?
That is the essential policy question. If the existing procedure is administrative, focusing on documentation, how do you integrate physical, mechanical redundancy? Maybe a lock and key system controlled remotely by the authorizing officer, or automated interlocks. Or how do you reinforce the psychological training building on the physics we learned today to ensure that the zero tolerance rule for a danger tag is absolutely unbreakable? You have to design a system that fails safe, even when the human element fails. That's your next deep dive.